Welcome back, students. In my previous videos, I explained you about the Cossel-Lewis approach to chemical bonding. Then I described about the Langmuir-Lewis approach and after that the octet rule. I told you that all atoms and compounds are in a kind of race to acquire 8 electrons or octet configuration in their valence shell. But we find that octet rule is not followed in many cases. There are exceptions to octet rule. And in this video, I will explain you about these exceptions or the limitations of the octet rule. The first type of exception to the octet rule is the incomplete octet of the central atom in certain molecules. In some covalent compounds, the number of electrons surrounding the central atom is less than 8. Keep this in mind, students. Now look at lithium. Lithium has only 1 electron in its valence shell. Beryllium has 2 electrons in its valence shell. Boron has 3 electrons and aluminium also has 3 electrons in its valence shell. So covalent compounds formed by atoms of elements with less than 4 electrons in their valence shells may not obey the octet rule. For example, lithium in lithium chloride has only 2 electrons surrounding it. Beryllium, which is the central atom in beryllium hydride, has only 4 electrons surrounding it. Boron in boron trichloride has only 6 electrons surrounding it. Since there are less than 8 electrons surrounding the central atom, these compounds violate the octet rule. Now, other examples of compounds which violate octet rule are beryllium fluoride, beryllium dichloride, then we have boron trifluoride, aluminium trichloride, and so on. Clear? So these are examples of molecules or compounds with incomplete octet which violate the octet rule. The second type of exception to the octet rule is the expanded octet of the central atom in certain molecules. Now, what is this expanded octet? In some covalent compounds, the number of electrons surrounding the central atom is more than 8, and this is known as expanded octet. And note that second period elements do not show expanded octet because they have only 2 shells. Okay, so elements in the third period and elements in the periodic table beyond the third period, they may show expanded octet in some of its covalent compounds. This is because they have 3d orbitals apart from 3s and 3p orbitals available for bonding. Okay, elements in the third period and elements beyond third period, they can expand their valence shell to accommodate more electrons. Okay, this is the reason why in a number of covalent compounds formed by these elements, there are more than 8 electrons surrounding the central atom. Examples for such elements, compounds formed by elements belonging to third period and beyond are PCl5, PF5, SF6, H2SO4 and so on, and a number of coordination compounds. Okay, you'll be learning about this in detail when you study +2. These compounds are called hypervalent compounds. See, here we have taken the example of PF5. Here you can see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons around the phosphorus atom. Okay, so this is a hypervalent compound with expanded octet. Now look at SF6. Here the central atom is sulfur and you can see that it is surrounded by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 electrons. Okay, there are 12 electrons surrounding the central sulfur atom. Clear? Now, SF6 is a hypervalent compound in which there are 12 electrons around the central sulfur atom and it shows expanded octet. Now, look at sulphuric acid. Okay, here you can see that the 2 hydrogen atoms, they have satisfied their duplet configuration. See, hydrogen has 1, 2, 1, 2. So, there are 2 electrons around hydrogen atoms. So hydrogens have satisfied their duplets. Now look at oxygen atoms. There are 8 electrons surrounding the oxygen atoms in all the 4 cases. So oxygen atoms also have satisfied their octets. Now look at sulfur atom. How many electrons are there around sulfur atom? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 electrons around the central sulfur atom. So this is an example of expanded octet, and H2SO4 is a hypervalent compound for this reason. Now let's try to understand how third period elements show hypervalency in its compounds from these examples. Here I have taken the examples of PF5 and SF6. Phosphorus pentafluoride is a hypervalent compound. Now let's see how phosphorus acquires expanded octet in this case. We know phosphorus is a third period element with electronic configuration 1s2, 2s2, 2p6, 3s2, 3p3. Okay, here we have 3 unpaired electrons in the valence shell of phosphorus. Suppose 3 fluorine atoms approach phosphorus. In this situation, each fluorine atom would have contributed 1 electron to each of the unpaired electron in the valence shell of phosphorus, and that would have resulted in the formation of PF3 molecule. But what we have here is PF5 molecule and not PF3 molecule. So something has happened in the valence shell of phosphorus. Let's check it out. Phosphorus is a third period element, so it can expand its valence shell to the 3d orbital in order to accommodate more electrons. Okay, and in this case, this is achieved when one of the electrons in the 3s orbital belonging to the valence shell of phosphorus jumps to the 3d orbital. Now look, initially we had only 3 unpaired electrons in the valence shell of phosphorus. Now after an electron jumped from 3s orbital to one of the 3d orbitals, we have 5 unpaired electrons in the valence shell of phosphorus. So in this case, what happened to phosphorus? It has expanded its valence shell. Okay, so this is how phosphorus expands its valence shell. Now in this situation, if 5 fluorine atoms approach the phosphorus atom, each fluorine atom would contribute 1 electron to each of the unpaired electron in the valence shell of phosphorus, and that would result in the formation of 5 PF bonds, which is nothing but PF5 molecule. Now if you see the number of electrons in the valence shell of phosphorus in PF5 molecule, see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 electrons in the valence shell of PF5 molecule. Initially, before bonding with 5 fluorine atoms, there were only 5 unpaired electrons in the valence shell of phosphorus atom. But after bonding with fluorine atoms, we have 10 electrons in the valence shell of phosphorus in PF5 molecule. So in this case, you can see that phosphorus has an expanded octet. It has more than 8 electrons in its valence shell. Okay, now look at this. Phosphorus belongs to 15th group. So it can have 2 valences, that is either 3 or 5, which means it can gain 3 electrons or it can share 5 electrons. Now what happened in this case? See, in phosphorus in PF5 has shared a total of 5 electrons. Okay, that is 1 electron each to each fluorine atom in forming PF5 molecule. So phosphorus chose the higher valence of 5 in forming the hypervalent PF5 molecule. Now look at SF6. Sulfur is a third period element with electronic configuration 1s2, 2s2, 2p6, 3s2, 3p4. Now there are only 2 unpaired electrons in the valence shell of sulfur. Okay, now in this situation, if 2 fluorine atoms approach sulfur, then each fluorine atom would contribute 1 electron to each of the unpaired electron present in the valence shell of sulfur, and that would have resulted in the formation of SF2 molecule. But what we have here is SF6 molecule and not SF2. So something happened in the valence shell of sulfur. See, sulfur being the third period element can expand its valence shell to the 3d orbital in order to accommodate more electrons. Okay, so this is achieved by sulfur in this case when one of its electrons belonging to 3s orbital jumped to one of the 3d orbitals and one of its electrons jumped from the 3px orbital to one of the 3d orbitals. So here initially before the jumping of electrons occurred, there were only 2 unpaired electrons in the valence shell of sulfur, but after the jumping of electrons has occurred, we now have 6 unpaired electrons in the valence shell of sulfur. So sulfur has now expanded its valence shell in order to accommodate more electrons. See, in this situation, if 6 fluorine atoms approach sulfur, what would happen? Each fluorine atom would contribute 1 electron to each of the unpaired electron of sulfur, and this would result in the formation of 6 SF bonds. So that's how SF6 molecule is formed, which is a hypervalent molecule with expanded octet. You can see that before bonding with 6 sulfur atoms, there were only 6 unpaired electrons in the valence shell of sulfur. But after covalent bonding with 6 sulfur atoms, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons in the valence shell of sulfur of SF6 molecule. So it evidently sulfur in SF6 has an expanded octet which has 12 electrons. Okay, now look at here. Sulfur belongs to 16th group, so it can have 2 valences, either 2 or 6, which means it can gain 2 electrons or it can share 6 electrons. What has happened in this case? Sulfur, you can see, it has shared a total of 6 electrons, that is 1 electron each to each fluorine atom. So sulfur chose the higher valence of 6 in forming the SF6 molecule. So this is all about the hypervalency exhibited by the third period elements in its compounds. Though sulfur is a third period element, it also forms many compounds in which the octet rule is obeyed. We just saw that elements belonging to third period and beyond, they violate octet rule. The compounds formed by such elements are found to violate octet rule. They do not obey octet rule, but sulfur here is an exception. Okay, now let's look at this particular example of sulfur dichloride. Let's study the formation of sulfur dichloride and try to understand how sulfur, being a third period element, obeys octet rule. The electronic configuration of sulfur is 1s2, 2s2, 2p6, 3s2, 3p4, and from this it is clear to us that there are 2 unpaired electrons in the 3p orbital of sulfur atom. Now, when 2 chlorine atoms approach sulfur atom, each of them, they contribute 1 electron to each of the unpaired electron present in the 3p orbital of sulfur atom. Pairing occurs. Okay, so bonding occurs, and this is how sulfur dichloride is formed. Clear? Now, let me ask you a question. Which is the valence shell of sulfur atom? Third shell, isn't it? Now, before bonding, how many electrons were there in the valence shell of sulfur atom? 1, 2, 3, 4, 5, 6. So 6 electrons were there before bonding in the valence shell of sulfur atom. Now, how many electrons are there in the third shell of sulfur after bonding with the 2 chlorine atoms? 1, 2, 3, 4, 5, 6, 7, 8. So 8 electrons are there in the third shell of sulfur after bonding with the 2 chlorine atoms. Now you can see that there are 8 electrons around the central atom in sulfur dichloride. Okay, so this is how sulfur, which belongs to third period element, obeys octet rule. The third type of exception to the octet rule is found in odd electron molecules. By now, we are accustomed to use the terms like lone pairs and bond pairs, right? However, in certain molecules, we find that the electrons may not be paired, isn't it? See, in nitric oxide, this electron is not paired. In nitrogen dioxide, see, this electron is not paired. Okay, so there are molecules in which the electrons may not be paired, and you may have odd number of electrons around the atoms of such molecules. So such kind of molecules are called odd electron molecules. For example, nitrogen combines with oxygen to form NO, and in this, nitrogen forms 2 bonds with oxygen. Here, oxygen, which had 6 electrons in its valence shell before covalent bonding with nitrogen, completes its octet after covalent bonding with nitrogen. That is, it has 8 electrons in its valence shell after bonding. See, let's count the number of electrons around oxygen. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 electrons around oxygen atom. So, okay, so it has completed its octet. But nitrogen, which had 5 electrons in its valence shell before bonding, used 2 of its electrons in the covalent bonding with oxygen. And it has one lone pair and a single electron that is left behind without bonding. So nitrogen in nitric oxide has one unpaired electron in it. So such a molecule is called an odd electron molecule. Now look at NO2 molecule. Nitrogen in NO2 has one electron over it. So NO2 is an odd electron molecule. Nitrogen combines with the first oxygen through a double bond. Okay, and we find that octet is satisfied in the first oxygen. See, let's count the number of electrons around the first oxygen. 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 electrons in the valence shell of the first oxygen atom. The second oxygen here has 6 electrons plus 2 electrons. That is, these 2 electrons are the shared pair of electrons. Okay, and these 2 electrons are from nitrogen. Okay, nitrogen contributed both the electrons to oxygen atom in the formation of this bond. Okay, here nitrogen and the second oxygen combines through a coordinate bond. Clear? Because let me remind you that a coordinate bond is a type of covalent bond in which the bonding pairs of electrons are contributed by only one of the 2 combining atoms. Okay, since this is a coordinate bond, nitrogen acquires a partial positive charge and oxygen acquires a negative charge. Clear? The fourth exception to the octet rule is found in compounds formed by noble gases. Octet rule is primarily based upon the fact that noble gases are chemically inert. This is because we know, isn't it, that noble gases are particularly stable due to the presence of what? Due to the presence of 8 electrons in their valence shell. Clear? Now, remember, I told you that all atoms are in a race to achieve 8 electrons in their respective valence shells through chemical bonding. They do this for what? They involve in chemical bonding in order to attain stability like noble gases. Okay, why are noble gases stable? They have 8 electrons in their valence shell. That is why they are stable. So, all atoms are in a race to achieve 8 electrons in their respective valence shells through chemical bonding in order to achieve stability like noble gases. If that is so, we may not strictly expect the noble gases to involve in chemical bonding. We don't want them to involve in chemical bonding. Clear? But noble gases like xenon and krypton, which are supposed to be inert, combined with atoms like oxygen and fluorine, and they form a number of compounds. These are a few examples of the compounds formed by xenon and krypton with oxygen and fluorine. Clear? So, the fourth exception to the octet rule is the formation of compounds by noble gases with atoms like oxygen and fluorine. The fifth limitation to the octet rule is that octet rule does not explain the shape of molecules. Clear? And the sixth limitation to the octet rule is that it could not explain the relative stability of molecules in terms of energies. See, we know that atoms combine, isn't it? When atoms combine, they do so by forming bonds. And when bonds are formed, energy is released. Clear? So, different amounts of energies are released during the formation of different molecules. And we know that a molecule is particularly stable only when its energy is minimum. Okay, But octet rule could not explain the relative stability of molecules in terms of this energy. So this is another exception to the octet rule. So octet rule cannot be the final rule because it has a lot of exceptions, and we just saw 6 of them. So with this, students, I wind up my video on limitations of octet rule. Thank you for watching.